Alright, good afternoon. This is a series of chemical breakdown of acids and bases, and we're getting to our situation of, okay, we know that H plus ions and hydroxide ions are what cause something to be basic or acidic. We've quantified it for the quantities to determine, are we actually acidic or basic. We've looked at how items make hydroxides and H plus ions, and now we're looking at that a little bit closer into some of the chemical reactions that occur here. So I have a few questions we're going to look at here, and our ultimate goal, I guess, for this PowerPoint was to start to understand a little bit more about equilibrium versus completion, and can I model what these things look like, acids and bases, like how these chemical reactions work. Okay, so first things first, what is the difference between something that goes to completion versus something that goes to what we call equilibrium? Okay, now completion is another way of basically saying what you've been doing with stoichiometry. Okay, if I have, let's say, now I'm just going to throw this out there, a strong acid goes to what we call completion. Okay, it's a reaction. Completion is a reaction that runs until something runs out. Okay, so we would have a limiting reactant. Okay, so with that being said, let's draw an ice table for this guy. We have HCl. Of course, we know the only way that an acid can produce H plus ions is via hydrolysis. I'm only going to draw one arrow here, H3O plus Cl minus. This thing only has a forward reaction. Now again, any reaction, depending on how fast it runs, we're not even indicating how fast this works. But even if it's running slowly, and if there's no reverse reaction, then, which we've talked about already, could be a reverse reaction potentially right here that would go backwards. So there is nothing here in that nature. So one that goes to completion, the reverse reaction essentially is nothing. So in some sense, eventually I'll lose all my reactants until something runs out, and I'll get all my products. It's like a rusting car. It's just a matter of time before a car rusts completely away to nothing, given the time. So let's say we have a 0.1 molar concentration of HCl. Well, water's going to be in excess at this point. I will lose some of it, but I'm just going to say it's in excess. You'll see why we dash that out in a moment. But it's going to lose all 0.1 molar down to 0, and therefore if I didn't have any of these to begin with, I would gain 0.1 molar, and I would gain 0.1 molar, and at this point, in the end, I have nothing of this, and only no reactants, and only these two guys are being produced. This is a classic limiting reactant, and this is something that goes to completion. Now, what about this idea of something that goes to equilibrium? This is a concept where I have essentially a tug of war, or I have a stalemate between two competing processes. And quite often, this is the bugaboo for many chemistry students in both high school and college. This is one of the main bugaboos for students in college. Alright, so equilibrium. It is literally peppered all over our society. You could think of equilibrium in terms of global warming. There are people that say, the Earth is just going through an imbalance, and eventually, as we increase the amount of carbon dioxide production, plants will then therefore eat more carbon dioxide, and we'll eventually get back to a balance point where we were before, and everything will be fine. Don't worry about it. There are other situations involving, let's say, political We got ourselves your Democrats, and you got yourself your Republicans, and they just sort of battle back and forth, and it's just eventually you strike a balance. Other than that, I mean, that's basically it. Okay, I mean, going back and forth. Something might happen which might drive it more towards the Democratic side, or something might happen to drive it towards the Republican side. It's just the same thing. But eventually, you look at the number of Republicans now versus the number of Republicans 10 years ago, probably not much different, or even 50 years ago. They strike a balance, and it pretty much, some people are leaving the Democratic Party, some people are gaining their you can't tell the difference. You could look at maybe the people inside of a city. People are exiting, people are leaving. But if you took a snapshot picture of the city, you might have X number of people in that city. And then hour later, take another snapshot of that city. Same X number of people. Because we have a balance between people exiting and people leaving. Two competing processes. We call this a forward reaction, and we have this what's called a reverse reaction. Okay? Quite often I will give an example. Okay, here's a typical example I might give. I have a fish tank. Okay, this is my fish tank example. And when I was first starting out as a teacher, I would, kids say, okay, well, I thought I have to have a fish tank. So I would get this fish tank, and of course the kids, they bought some fish, I bought some fish, and this particular guy, okay, fish are swimming around, things are all good and dandy and all of a sudden, because you're very busy, especially as a new teacher, I start having algae grow up on this thing. So we're going to look at a balance, equilibrium between the births and deaths of algae. Okay? So arrow to the right means deaths, arrow to the left means births. Now as I got started with this fish tank here, I didn't see anything occurring. Just fish swimming around. But all of a sudden, as time goes by, the births of the algae really start to pick up. I start seeing algae pretty much just caking the beginning of this thing. And at this point, I didn't really notice any deaths. I mean, you have to know that the algae are dying all the time, right? So, but at some point, all you notice are the deaths, or sorry, the births. Now, anytime, key indicator is anytime you see change occurring, that means you're not at equilibrium. Okay? Equilibrium is a stalemate. I'm not at equilibrium because I have lots of births of algae. So anyways, time goes by, and it seems like, okay, at some point here, and maybe the water dropped a little low too, and kids would complain, the fish are being abused, and I'd be like, well, it's privacy. They like this. It keeps, you don't want to see kids, it's privacy. It reminds them of home. Anyways, at some point, you have this algae here, and it appears at some point that there's no more births occurring. It's just caked. So I have reached a point of equilibrium where my births, I'm just going to use the arrows, are equaling my deaths. And it appears that nothing is happening. And that's my new form of equilibrium. So that stayed like that for quite some time. Well then, some students, being concerned about the welfare of the fish, went and bought me 2 algae eaters. And they're little sucking little things. There were 2 of them. And they must have thought they hit the jackpot. Okay? But all of a sudden, this equilibrium was now disturbed. And I have a situation here where all of a sudden the deaths just increased massively. Were there any births of algae at this point? Well, yes, of course there were. I mean, hard not to be. But you couldn't tell anything. All you saw was algae disappearing at a pretty random rate, a pretty fast rate. And all of a sudden, this stuff just starts wiping away. And in a very short time, surprisingly actually, the algae was just gone. And I struck what appeared like there was nothing happening anymore. The algae eaters are there, but I struck a new balance with my algae eaters where the births and deaths appeared to be balanced. I know algae are being born, I know they're dying, but I couldn't tell the difference. So at some point in this situation, I struck a new balance. And that stayed for a while until, sadly, one of my algae eaters died. And then the other one, being so lonely, died as well. And we struck once again, a new situation occurred where the algae births start to pick up. Okay? And now I have again all of this algae forming here, and once again come to this caked point, and I return back really to my old equilibrium. Okay? So this is an example of equilibrium. Another example of equilibrium. Okay, we'll do this one, and then likely video will be over. There's a little concept here where, let's say, okay, you have a building. Now, this is our school here. Let's say we have our school here. And our school's got a flat building, so about like this. And at night, they tend to turn the heat down. They turn the heat down. So during the daytime, okay, so from, let's say, 6 until 4 usually, they'll have the heat on if it needs to be. And then at that point, it really drops off into being cold at night. So I always talked to my grandpa, and he always said, this is a waste of energy. You know, all you're doing is allowing all your stuff inside here to get cold. It's getting cold, all your chairs and everything gets cold, and then all you gotta do is reheat that stuff back up, which of course would be a waste of energy. You'd be better off just leaving the heat on. And that way you wouldn't have to reheat these things. Okay? And I'm sure he didn't want an explanation of equilibrium, but here's the reason why they turn the heat off. You have a substance, this doesn't have to be a school, it could be anything, okay? And this item is going to be exiting energy, okay, if it in fact has a higher temperature than the surrounding items, okay, based off temperature. If this temperature is higher than this temperature, then energy is going to exit the system. You know, it could be insulated, which might slow it down, but either way, eventually, given time, this item and this item would be the same temperature. I could take a beaker of hot water, or let's just say cold water, 25 degrees Celsius, and I drop a hot block into this thing, 100 degrees Celsius, drop it in here, and eventually this will radiate all the energy to the surroundings, and they become the same temperature. The thing about this is that the larger the difference in temperature between these two, the greater the change in energy. All right? So if this thing is really hot, okay, or if it just is super cold outside, then the rate at which the energy changes is much greater. And you might note that, again, at some point, if we just were to allow them to become the same temperature, the temperature of the inside would start to cool. So this would cool down, cool down, cool down, and eventually this slows down, this slows down, this slows down, and now they're the same temperature, and we have a balance. Now, technically, at that point, we have the same temperature, we're at equilibrium. Where technically they're the same temperature, so either is there no energy changing back and forth? No, there's still energy crossing back and forth, but we could have energy entering or energy exiting that building, and at this point they're at equilibrium. So because energy is a quantifiable amount, it is like money, all right? It doesn't matter if you cool this inside down, because what we're doing is from 4 until, let's say, 6 o'clock the next morning, we're dropping our temperature to be closer to the outside, and therefore my heat exchange is less. All right? and therefore I'm closer to my equilibrium. I'm not at equilibrium, I'm closer to it, and therefore the exchange of heat from inside outside is smaller than what it would be if I were to have left the heat on. Left the heat on, we have a very large loss of energy, whereas in this case, lowering the temperature is much more ideal, because even though I'm cooling down the inside, the time that I'm cooler, I'm losing less energy. And that is another example of equilibrium, of gaining and losing energy. We'll stop there for today. The main objective today, okay, maybe we get all these guys here, we'll get on the next video, is essentially what is the difference between completion and equilibrium. And we've already discussed an idea of this involving acids, and we will go to that more next time. Thank you.